Hello class, we'll be talking about the quantum analog experiment. The idea behind this experiment is we want to study the behavior of quantum states with a classical experiment, something that we can achieve classically. What this experiment does is tries to simulate an analogy between sound waves, standing waves, uh, inside a tube. And quantum energy states as an example. We'll talk about the infinite square wave. Okay, so how does this experiment do it? Well, we talk about the formation of a standing wave. So the apparatus will work as follows. We have a speaker which is generating sound waves at a frequency f, let's call it. And so we have a microphone, and this is R2 of length L, and at the end of it we have a microphone. So that's how we're gonna record the signal. Okay. So this speaker sends sound waves that will be traveling through the tube, and in there they will be trapped and will reflect back and forth. So once they make it to the wave, they will be recorded by the microphone, but they make it back again. Okay. So what happens? So when a sound wave here, let's call it wave 1, gets emitted, it's gonna reflect back, and then I call it now the wave 2. It's gonna make it back, be reflected, then another wave is emitted by the microphone, by the speaker. And when when waves 2 and 3 meet, they are in phase, meaning that if they are in phase, they're gonna interact constructively. Once that happens, their amplitudes combine, and so as a result, you get a stronger sound wave. So you record a stronger value. Does this happen for every frequency? No, that's not the case, because as you might recall from the mechanics class, or the condition for to have standing wave is the product of twice the length is equal to nc, where c is here is the speed of sound, over the frequency at which these sound waves are emitted, or we can simply say it's n times the wavelength. Okay, so we satisfy this condition, and this only happens when you have multiples of n. How do we translate to the quantum case? Well, we have the following. So you have here, plotted here, you have a potential as a function of x, and we have our x-axis here, 0, we call that the origin, and in between 0 and L, you have a potential that goes to infinity at those boundaries. And you can think of having a particle stuck between these walls, because it cannot get out, because this is an infinite potential, right? Alright, so how does this relate to the case I just talked about? So now think about when we get what we call eigenstates. So basically now this, instead of talking about resonance, what you can consider to be a resonance, we're talking about the energy states here. And so because they are quantized, they don't just have any energy, they have values of energy. And if you were to write the equation for that, I can put all the constants, but the importance is we have an relationship with n squared, and energy is proportional to the n squared, where n goes from 1 to infinity. And so with the help of the resonances, we can get an idea of this kind of behavior from the quantum world with something that you can actually see. This is a simple explanation. On the next video, I'll talk about the experimental setup.